Okay, tonight's lesson is 6.6 and it's on the differentiation and integration of Laplace transforms. We begin here with the definition of the Laplace transform of the function ft. Of course, that's capital Fs, and the definition of the Laplace transform is right here. What we want to do then is take the derivative of the Laplace transform. I want dds of Fs. And this may seem complicated, taking the derivative of an integral, but it really isn't, because most of this integral is constant. F of t dt, that's all a function of t, so the derivative with respect to s treats all of this as if it's a constant. Really, the only thing that's a function of s is e to the negative st, and its first derivative would be negative et times e to the st. So it's still the integral from 0 to infinity, negative t e to the negative st, f of t, dt. So this is the first derivative with respect to s of the Laplace transform in the form of the definition of the Laplace transform. Well, if we look at that, I can move the negative outside. And then I can move the t in front of the ft. So it's e to the minus st times t ft dt. And of course, this would be the Laplace transform of t ft. And that's the answer. F prime of s is equal to the Laplace transform of t ft. Oh, and there's a negative in there too. I pulled the negative out, so it doesn't matter which side the negative goes on. We'll put it over here, but it's the Laplace transform of t ft. Now, this has applications because there are times when finding the Laplace, the inverse Laplace transform of a function might be difficult, but finding the Laplace transform of its first derivative is a whole lot easier. So if we want to undo a Laplace transform, sometimes differentiating it first makes a really big difference. And we'll look at a couple of examples of problems like that. Of course, we can turn this guy inside out too. That means t ft is also equal to the inverse Laplace transform of negative f prime s. And of course, I can put the negative on either side of that too, okay? So these are both true relationships, and you'll use these as your differential relationships, okay? In the same way, there are integral relationships. I'm not going to go through the derivation of those, but the integral relationships look just as clean and easy as these. If I want the Laplace transform, or excuse me, if I want the integral from s to infinity of f s tilde ds tilde, and again, notice we're using another dummy variable, so we're going to replace fs with fs tilde, and then we're going to integrate it from s to infinity. That will leave it as a function of s. So this will end up being the integral of fs, okay? Well, what's that equal to? Unsurprisingly, this is the Laplace transform of f of t over t. And again, if you want to look at the derivations for these, be my guest. The flip side of this is also true. The inverse Laplace transform of this integral from s to infinity of fs tilde ds tilde, brackets around this, and that of course is equal to f of t over t. And again, in this case, you would simply take the Laplace transform and you would integrate it, and then take the inverse Laplace transform, and that'll find your f of t. Or you might have something that's already in this form, in which case it will already be the Laplace transform of another function. You can apply the inverse Laplace transform and immediately find it, okay? So those are your two options. Okay, so we're going to utilize these in order to work on some interesting transform problems. There is an obscure application to a single kind of differential equation, which we're not really going to focus on. It's only one kind of equation, and so we're going to kind of skip over that for this lesson. It might crop up again for you later, but it won't right now. So let me show you the 2 example problems that are similar to tonight's homework, okay? Okay, in the first kind of problem, and these are both sort of inverses of each other, given the Laplace transform of a function, find the function. Now, normally this is pretty easy. This is just looking on the table. The problem is some of the FS's are going to be a little bit more complex. So let's take a look at the first one. Fs, in this case, is going to be the natural log of s over s minus 1. And of course, nothing on the table has a natural log in it. And so we know immediately I'm not going to just be able to use the table to convert this to the f of t that gave us this as the transform. So what do we do instead? Well, I suspect that I'm going to go ahead and take the derivative of this and see what that yields. To do that, what I first want to do is apply a rule for logarithms and say this is the ln of s minus the ln of s minus 1 quantity. And now I can go ahead and find f prime of s. So that will be the derivative, and of course the derivative of the natural log of s is just the derivative of s, which is 1 over s, minus, and the same thing here, derivative of s minus 1 is still 1 over s minus 1. And you can see immediately that taking the derivative of this turns it into something that looks very much like a Laplace transform. So now what we can do is apply the inverse Laplace transform to this guy. So I can say, hey, let's do the inverse Laplace transform of f prime of s. And that, of course, is going to be, well, 1 over s, that's just 1. And 1 over s minus 1, that's just e to the t. So minus e to the t. And of course, what is the inverse Laplace transform of f prime of s? Well, we just did that. That was equal to negative t f of t. And that means that f of t is going to be this guy divided by negative t. So it'll flip the sign around. It'll be e to the t minus 1 divided by t. And this is the function that has this as its Laplace transform. So that's the way you can use differentiation of Laplace transforms to convert into and out of the transform form. All right? Some of tonight's homework problems will be like this. You'll be taking FS's and finding FT's from them. Some of these might end up being a product, so you'll be using convolutions, but some of them will turn out to be differentiations, okay? So don't be surprised if you do maybe see a convolution in there too, all right? Okay, the second kind of problem then is the reverse of this. And of course, the exact reverse of this would be to take the Laplace transform. Given ft, find fs. Now, once again, you might think this is easy. I can just plug the ft into the integral form and go ahead and find fs directly. And of course, that is okay as long as you can actually perform that. But what you might want to do is go with one of these derivative integral forms. The one we want to do is this. F of t is actually equal to t cosine of omega t. Now, be my guest to plug this in to the integral form of fs. By doing that, you're basically going to have e to the minus st, t, and cosine omega t. And that to me is going to look like a really, really unpleasant integration by parts. So we're not going to go there. Instead, let's look if there's some other model we can use. Hey, the good news is one of the forms we saw was t f of t. So maybe that's what we're going to do here. If I consider taking the Laplace transform of f of t, then what that really is the Laplace transform. Oh, let me put the symbol in. The Laplace transform of t cosine of omega t. And in essence, this is really just going to redefine our f. Our original f was this. Our new f is just the cosine of omega t, because look, the Laplace transform of t cosine omega t is like taking the Laplace transform of t f of t. And of course, we know that the Laplace transform of t, f of t, is equal to negative f prime of s. Now, this particular fs was based on whatever this particular ft is. So I'm going to ignore the original definition for ft because the Laplace transform of that original ft produced a Laplace transform of t cosine omega t, or t times a new f of t, of which this fs is the Laplace transform of. So let's find fs, assuming that ft was cosine of omega t. Well, fs, assuming ft is cosine of omega t, is just going to be the Laplace transform of cosine of omega t. And of course, that's right on the table, easy enough to look up. Cosine of omega t, s over s squared plus omega squared. Now, that's not the answer. Remember, Laplace transform of f of t is going to be the negative of f prime of s. In order to find f prime of s, I need to take the first derivative of this with respect to s. And unfortunately, it's a quotient rule, and they're not always the easiest. I want to take the denominator times the derivative of the numerator. That's 1, so it's s squared plus omega squared times 1. And then we're going to subtract the derivative of the denominator to s times the numerator, s. And then that's all over the denominator squared, s squared plus omega squared, and the whole thing squared. Okay, this is going to be s squared plus omega squared minus 2s squared. So it'll really be negative s squared. I'll just pull the negative out front, and it'll be s squared minus omega squared divided by s squared plus omega squared squared. Well, if this is f prime of s, and I want negative f prime of s, I can just move the negative there and make this positive. And this guy right here, that's the Laplace transform of our original question. So this is then the Laplace transform of f of t. Now I know it seems tricky because it feels like we took the inverse Laplace transform of cosine omega t alone. Keep in mind that the Laplace transform of our original f of t produced a form whose f prime of s was only cosine of omega t. But because our original f of t gave us that form, the inverse Laplace transform of f prime of s actually does provide for the Laplace transform of the original function. So don't worry, it isn't as if in redefining f we've made some mistake here, right? Okay, armed with this material, you guys should easily be able to finish tonight's homework, which is to take a few FS's and turn them into FT's, and a few FT's and turn them into FS's. Also view this as a review homework for doing convolutions and just for applying the general technique for Laplace transforms, all right? Again, it's a bit of a break from differential equations because we're not actually applying anything we learned today to their solutions.